sessão da tarde. Então, it's a pleasure and honor to introduce you to Serge Vaudenay. Let me read here. Serge Vaudenay entered at the École Normale Supérieure in Paris in 1989 with a major in mathematics. He received his PhD in computer science from University of Paris 7, Denis Diderot. In 1995, he subsequently became a research fellow at CNRS. In 1999, he was appointed as a professor at the EPFL, where he created the Security and Cryptography Lab. He works on cryptography and the security of digital information. Most of his work relates to security analysis and provable security of cryptographic algorithms and protocols, especially in symmetric cryptography, post-quantum public key cryptography, RFID protocols, and distance bounding. He wrote an essay on cryptography in French, published by PPUR, and a textbook on cryptography, published by Springer. He was program chair of several research conferences and workshops: ACNS 14, IndoCrypt 13, Africa Crypt 12, SEC 11, Africa Crypt 8, Eurocrypt 08, 06, MyCrypt 05, PKC 05, quite impressive, SAC 01, and FSC 98. In 2007 to 12, he was an elected director of the ISCR. So please welcome Professor Serge Vaudenay.
Thank you very much for inviting me. Today I'd like to talk about format-preserving encryption. So that's a joint work with my colleague Betül Durak. So in this talk I will... Okay, it's off now. Okay. In this talk I will first introduce what is format-preserving encryption, then present some work that we did. So essentially we found some attack on first on four round Feistel schemes, because we will see that format preserving encryption are based on a Feistel scheme. Then we will move on to an attack on a FF3 algorithm, which was proposed as a standard for format preserving encryption, and present some new generic attack on a Feistel scheme. So first, what is format preserving encryption? So format preserving encryption comes from a natural evolution of encryption methods. So it's an encryption method, and if you think about it, at the beginning of the encryption method that we know, at the beginning was DES. So DES was a block cipher. Block cipher are used to encrypt blocks of data, blocks of 64 bits in the case of DES. And with this block cipher, you can only encrypt the block. So what do you want to do if you want to? What can you do if you want to encrypt a message which is a sequence of blocks? If you want to encrypt a longer message than 64 bits, then you use a mode of operation. With the mode of operation, you can encrypt sequences of blocks instead of just one block. Then you have a problem if you want to make sure that the length of the ciphertext is the same as the length of the plain text. So imagine that you want to encrypt a message which has 300 bits, and you don't want to pay for extra bits so that you will complete the last block of the message. So for that, at the beginning we had block ciphers. Now block cipher encrypts typically blocks of 128 bits. Then we have the notion of length-preserving encryption. So length-preserving encryption can encrypt a message which has an arbitrary length, and they will encrypt into a message which has exactly the same length. And now we want to do something even more precise, which is the notion of format-preserving encryption. So in a format-preserved encryption, you don't only want to encrypt the bit strings, you want to encrypt some data which follows some format, which has some format, and you want to make sure that the ciphertext will follow exactly the same format. So for instance, you want to make sure that if you encrypt a date of birth, it will be encrypted into a date of birth. If you encrypt a zip code, it will be a zip code. If you encrypt a credit card number, it will be a credit card number, and so on. So there are many reasons why we would like to do so, not only to save a few bits, but you have lots of problems with legacy systems. So imagine that you have a company, and your company invested quite a lot into some information technology structure. So you have a huge database, you have lots of equipment which synchronize to this database. When you first develop it, you didn't think about security, and then came security problem, and suddenly you wanted to add security on top of your system. So if you have a database with lots of fields of different format, typically you want to encrypt every field of the database. But if you have a software which can only tolerate dates of birth or credit card numbers, if you want to enter a bit string, you will have problems because it will be rejected by your software. So you would like to use the same software, but to use data which is encrypted. So you want really to be transparent with the information technology that you're using. There are also some other cases which are very common, like for instance, people work on smart cards. So there was a smart card technology, people invented smart cards, they put also PIN codes to unlock smart cards. They design lots of protocols. So typically when you unlock a smart card, you have to enter a PIN code into a smart card reader. And the PIN code that you type will be sent to the smart card, and it will be communicated through a protocol which is quite standard. So now there is a requirement from standardization bodies which says that now you cannot transmit this PIN code to the smart card directly, you have to encrypt it. But the protocols are not made to encrypt the bit strings, to transmit bit strings. They are meant to transmit only PIN codes. So you want to make sure that if you encrypt a PIN code, it will still be a PIN code. So that's why now we need standard for format preserving encryption. So companies use quite expensive software. They don't want to replace this software, so they just want to encrypt on top of the software. And you also have standards, and you will be bound to using these standards, even though you want to encrypt data. So a simple approach for format preserved encryption is to first define which is the domain of your encryption. So what is the domain of your formatted information? And try to enumerate elements in this domain. So the naive solution consists of assuming a numbering of all the elements in your domain, and to design an encryption function which can encrypt numbers. So if you have a domain of size n, you want to encrypt all the numbers between 0 and n-1. So that would be a natural approach. So you just assume that there is one way to convert numbers into your formatted string, and your formatted string into a number. Now, if you have some data which is not so easy to enumerate, but you can check the validity of your standard or of your data, another way can consist of trying to upper bound to have n which is a bit bigger than your domain size, to define an encryption on a domain of this size, and then to do what people call shuffling. So you assume that you have a permutation phi on, say, Zn, so that's all the numbers between 0 and n-1. Your domain, your encryption domain is a bit smaller than that, a bit smaller than n. So what you will do to encrypt on your domain is that so your domain is D. You will define this encryption function by saying that an element of D is encrypting by iterating this permutation phi enough times until you end up in this domain. So what you do is that you convert your value into an integer, you apply the function phi, maybe this after the application of this function file, you don't have data with a valid format, so you continue to encrypt and encrypt and encrypt until you reach data which has valid format, and you say that's the encryption of my original X. So that's a very common method to define on arbitrary domain when you can have an upper bound on the side of this domain. So that's how we can do. So the bottom line is that we don't need to define an encryption method on arbitrary domain. We just need to define. We don't just need to define an encryption method over the integers of not arbitrary n, but a few n's, which will be easy to use with this method. So in what follows, what we will do is that we will define some encryption method on domains which have perfect squares. So what we will consider are Zn square, essentially. We will define an encryption method on Zn square. So we'll define encryption on domains which are perfect squares. So then we have to consider also domains which are very, very small. So now we don't want to encrypt the data which is at least one block of 128 bits. We would like to encrypt a message which is only 2 digits, like a number between 0 and 99. So if we encrypt on a domain which has this very tiny size, we have more privacy problems than before. So typically what can happen is that equality of messages will be leaked. So if you have a deterministic encryption, enc, and if you have two messages x and y which are equal, after encryption they will still be equal. So deterministic encryption reveals equality. And if you have a very, very small domain, you're more and more likely to have equalities, and just by looking at equalities, you will leak too much information. So to avoid that, we use what we call tweaks. A tweak is some extra input that we input to the encryption to make sure that if you change a tweak, the encryption will be completely different. So you will separate domains by using tweaks. So a tweak can be a public information which is associated to the data, or something which is available in general when you encrypt and decrypt, and it's something which is also visible in clear. It can be controlled by the adversary, etc. So for instance, if you want to encrypt a credit card number, so this is a credit card number that I generated recently. If you encrypt this credit card number, you can encrypt with a tweak set to the name of the holder. So on a database, if you encrypt this way, you will make sure that you have less problems when you compare the encryption using different tweaks. Another method which have been seen as well is to encrypt only the private part of the credit card number. What is typical in a credit card number is that the first digits here represent the issuer of the credit card. So normally they are not so private, so it only represents the issuer. And the last one are often revealed in clear, just for the user to check that it is the correct credit card number which is used. So we can imagine also that this non-sensitive part of the credit card number is used as a tweak, and what we encrypt is only the private digits which are in the middle. So here we have only 5 digits to encrypt, so we have very, very small domain, and we won't have problems by equalities of these numbers because we will use tweaks which are different from one credit card to another. So if we have credit cards which came from the same issuer and with the same last 4 digits, then we use the same tweak. But in that case, we won't have equalities with the middle bits. So a tweak, it's something which can be reused. So it's different than a nonce. A nonce is something that you must not reuse. But a tweak, it's okay to reuse. Maybe you should limit the number of usage of the tweak, but it's okay to be reused. It can be sent in clear or publicly available. So in particular, the adversary knows which tweak is used. And also sometimes the adversary can also influence the tweak, so you can have some chosen tweak attack. So in the adversarial model, you can imagine that the adversary can control the selection of the tweak. So what we want to have a format preserving encryption, finally, is to have a deterministic tweakable encryption on a domain which has a form Zn square. So we'll encrypt pairs of numbers between 0 and -1. So the input consists of a secret key, a tweak, and a plaintext which consists of 2 numbers between 0 and -1. And the ciphertext will be 2 numbers between 0 and -1. And n square can be very small, so we have to be careful when we want to analyze the security. So that's the method to design format preserving encryption, and this method have been standardized by NIST last year, by NIST and by ANSI and other standardization bodies. And this NIST has issued a standard with 2 algorithms, so I will come back to this. What was used in this standard was a construction based on Feistel scheme. So Feistel scheme looks like this. Imagine that you have your input as an input, you have 2 numbers. So L0 and R0 are 2 numbers between 0 and n-1, so they live in Zn. You have a key, you have a tweak. So key and the tweak is entered in every round, and at every round you have also an index number, which is entered to the round function here. So what you do is that you take the right number, you map it through this function f with the key, the tweak, and the index number. And the result of this function is added to the left number with the addition modulo n. So after that, you iterate, and at the end, you obtain your ciphertext, which consists of these 2 numbers between 0 and n-1. What is interesting to see is that this function f can be anything. So you can use any function here. It doesn't need to be a permutation, and the magic of this Feistel scheme is whatever you put here will be a permutation, so it will be an encryption method. So it's easy to realize that if you start from the output here, so if you know the key, the tweak, and the output, you can process backwards. So you can take the left value here, map it through this function, and subtract it from the right value here, and iterate. So that's the decryption here. So you start from the bottom and you compute the plaintext. So that's for the Feistel scheme. Now, there is a lots of literature about the analysis of the security of Feistel schemes. So this literature is quite old, and due to the recent standard, people started to look again at Feistel schemes. So what can we say is that first, imagine that you have R rounds in a Feistel scheme. You have domain of size n squared, so you encrypt pairs of numbers between 0 and n-1. And imagine that the adversary can mount an attack with Q plaintext ciphertext pairs. So it can be chosen plaintext, non-plaintext, etc. But imagine that you have Q pairs. What we can already see is that if Q is equal to Rn/2, from information series, this is already insecure. So here we try to see what is the unconditional security of Feistel scheme. So in theory, with Q equal to Rn/2, it is insecure from an information series viewpoint. So to realize this, you can see that if you have R rounds with a domain of size n squared, you have R functions mapping a number between 0 and n-1 to 0 and n-1. So this function is defined by n values in the n. So your Feistel scheme is defined by Rn values in the n. So if you have Q plaintext ciphertext pairs, you have 2Q equations over the n. So if you make sure that 2Q is equal to Rn, normally you can solve it from information theory, and it is insecure. So this is already a bound to say what we can expect for unconditional security. Now, we cannot prove security for Rn/2. What we can prove is that when Q is negligible against n, when it's much lower than n, if you have 4 rounds, it's secure against non-plaintext attack, with 4-round Feistel scheme is secure against non-plaintext attack if you limit Q the number of plaintext ciphertext pairs compared to N. With 5 rounds, it's secure against chosen plaintext attack, and with 6 rounds, it's secure against chosen plaintext and ciphertext attack. But you don't have any proven security when, say, Q is equal to N. If Q is equal to N, it's open. It's an open problem to see if it is secure or not. Okay, so we don't know if it is secure. We just know that for Rn over 2, in theory, it is insecure. Okay, so that's the theory about Feistel scheme, and we will see how it is used in practice with format-preserving encryption. So in the NIST standard, so it's SP838G. It was published last year. So it's very recent. So there were 3 proposals to this standard, FF1, FF2, FF3. And in the standard, they have only taken FF1 and FF3. So FF1 and FF3 are 2 encryption methods, 2 format-preserving encryption methods. There are tweakable Feistel scheme with modular addition. It's balanced with 2 branches. In a standard, they require that n square is at least equal to 100. So it means that n cannot be below 10. Okay, so but even if you have a domain of size 100, it's already very, very small. For FF1 and FF2, we use 10 rounds, and for FF3, we use 8 rounds. So FF3 has less rounds than the other. Typically, what we use as a round function is a round function defined based on AES. So it's a bit surprising. So you use a very strong, well-established block cipher to define an encryption method which on a very tiny domains. So you have this round function AES based on the secret key K, where and to compute the image of X, what you do is that you first pad this message X, you pad it also with a tweak with the index number, you apply AES, so you hope that all this will take one full block of 128 bits, and you reduce it modulo n to define this round function. So that's the typical construction in FF1 at least. In FF3, we will see that it's a bit different. So here we don't concatenate the tweak with the index number, we XOR it, and we will see why it is not a good idea. So the security objective for this standard is to have 128-bit security, whatever it means, because if you have a domain of size 100, I'm not sure what it means to say that we have security of 128 bits. So nevertheless, we try to make sure that there is no attack with complexity below 2 to the 128, which is at least not trivial, but again, there is no real formal definition of what it means to be secure. So what can we have as an insecurity result? First, there is a trivial codebook attack. So if you have a chosen plaintext attack and you're allowed to query n square plaintext ciphertext to get n square plaintext ciphertext pairs, you can just dump the entire codebook of your function, and then you can decrypt whatever you want because you have the entire codebook. Okay, so that's a trivial codebook attack. So what we would like is to have no attack which is essentially better than this one. There was an attack proposed by Bellare, Huang, and Tesaro last year, which uses more data, but this attack is not so trivial, and we will see in the next slide how it works. It is actually quite a significant attack, because this attack uses many tweaks. So it works even though, by design, you cannot encrypt too many messages with the same tweak. Okay, so if you limit the number of usage per tweak, then this attack cannot work, because this attack uses only with one tweak. But if you have a limited number of usage per tweak, you can use this attack by Bellare, Huang, and Tesaro. This year at a crypto conference, my colleague and I presented an attack on FF3. So we will see that FF3 is badly broken, but can be repaired. So we'll see it later during this presentation. And what is new is that we figure out that for very tiny values of n, we can have also insecurity result even for FF1 and all the Feistel-based constructions. So we have to be careful with very small domains. So how about the attack by Bellary, Wang, and Tessaro? So it's based on an observation which is due to Jacques Patarin from the 90s. Jacques Patarin observed that if you have if you encrypt with two messages and the difference of the right part of the two messages is 0, so it means that the right part is the same for both messages, then the output delta LR is most likely to be equal to delta L0. The difference between the two values of LR is most likely to be equal to the difference of the two L0. So if you, I can show the picture here. So if you take the two messages with the same value here, for sure here the delta, the difference that you will observe here, so the difference you will observe here will be equal to the difference you will observe here, because here you have twice the same value, so the delta is 0. If the delta is 0 here, the delta is 0 here, so the delta plus 0 is the same here. Okay? So after one round, the delta here is the same as the delta here. What can happen after, say, 3 rounds is that the delta here can be by some kind of chance equal to 0. So imagine that the delta after the second round function f, the delta is 0. So you have two values here, but they enter into collision through this function, and the delta is 0. Then the delta which is here will be equal to the delta L0. Okay, so that's one case. So this can happen randomly. The probability is typically 1 over n. If the delta is not 0, so then the delta here will be non-zero, but there is a second chance to have the delta equal to 0. So it means that you will have 2 chances out of n for the delta here to be equal to the delta there. So it means that the delta is more likely to be equal to the original delta. So it's biased. So that's what Patarin observed, and it was used. By Bellary, Wang, and Tessaro to mount their attack. So typically what they say is that if you take 2 messages with the same right half, and if one message is known, and you don't know the second message, so you know that the 2 messages have the same R0 in common, but for one you know L0 and for the other you don't know L0. After encryption with the same tweak, you can look at the delta of LR, the delta left half of the ciphertext, and you can do some statistics by using many tweaks. And by doing some statistical analysis, you will deduce what is delta L0, and since you know one of the two L0, you will deduce the other. So if you do some analysis, you will realize that the data complexity is equal to this value. It's something small multiplied by n to the power r minus 3. And the time complexity is linear in the data complexity. So that's essentially the attack by Bellary, Wang, and Tessaro. So in our attack, so that's a decryption attack with many tweaks and with related message. In our attack, we don't have the same attack model at all. So what we want is to make an attack with data complexity lower than n squared, because we want to compare to the codebook attack. And we want to reconstruct the entire codebook, actually. So with less data than what is necessary for the codebook, we want to recover the entire codebook. Actually, we won't recover the codebook. We will recover the round functions. So we want to recover the round functions which are in DS. So imagine that n is small. We want to recover the tables of the round function. But actually, we won't recover exactly the round function, but one equivalent set of round function, because we realize that you can have several sets of round function which define the same codebook at the end. So we just want to recover one of them. So to see that why 2 sets of round function can define the same encryption function, just take this 8-round Feistel scheme here. So you have 8 rounds defined by 8 functions from F0 to F7. So imagine that you have this Feistel scheme, and now you will construct an equivalent Feistel scheme with different round function, but it will define exactly the same encryption function. So for that, what you can do is that you pick arbitrarily some delta 0, delta 1, delta 2, etc. And what you do is that you define here a function f prime 0, which just transform f0 by adding at the output some delta 0. Okay, so here you add some delta 0. This delta 0 which is added here, you will subtract here, and then you will apply f1, and at the output of f1 you will add delta 1. This delta 1 you subtract here, etc. And like this, you make sure that the computation will define exactly the same encryption method. Okay, because the values that we will have here when we do this change will be the same value as before plus delta 0. And after here, because here we added delta 2 minus delta 0, it will be the same value as before plus delta 2. And after here, it will be the same value as before plus delta 4. And here we subtract delta 4, so it's the same value as before. Okay, and it's the same on the right part. So if you take this constant, you define these functions like this, and you have exactly the same encryption function. What it means is that for any set of input and output for R-2 rounds, there is a set of function f prime 0 to f prime r, which map the xi to the yi, and which define exactly the same encryption method. So for every set of function, you can define an equivalent set of functions mapping some arbitrary inputs to some arbitrary outputs for one point in each round except 2 rounds. Okay, so that's for R-2 rounds in total. So our attack will be based on this observation to speed up the to improve the complexity. So I come now to our attack. So first I will present some attack on 3 rounds and 4 rounds in a generic Feistel scheme. So remember that in the NIST standard we use 8 rounds or 10 rounds, but we will start with 3 or 4 rounds. So this is a list of attacks which are known. So what we'll present here is that our attack on 3 rounds and 4 rounds. So our attack is a non-plaintext attack on 3 rounds, which has time complexity n and data complexity n. On 4 rounds, before there was an attack by Biryukov, Laurent, and Perrin, which was a chosen plaintext and ciphertext attack, which worked with this complexity. But what we need is to have a non-plaintext attack. So their attack was a chosen plaintext and ciphertext attack, and we needed a non-plaintext attack. So we have found a non-plaintext attack. The complexity is higher than their attack, but it is non-plaintext attack, and it will be quite useful to have the attack on FF3. And this attack can be also expanded to more rounds with a higher complexity. Okay? Let's start with 3 rounds. So this is a Feistel scheme with 3 rounds. So remember that we want to have non-plaintext attack. So we have a set of non-plaintext and ciphertext pairs. So imagine that we have this set of x, y, z, t tuples of size some value theta multiplied by n. Okay, so imagine that you have this set of plaintext ciphertext pairs. We want to recover the function f0, f1, f2. And we will recover an equivalent set of function f0, f1, f2. And remember that for f0, you can take an arbitrary input, an arbitrary output, and you will find an equivalent tuple of function mapping this arbitrary input to the arbitrary output. Okay, so you can fix this function. So what you do to attack it is that first you start with an arbitrary y value, and you take the subset of the tuples which have this value y. We choose this value y. So since you have a set of size theta n, and you have n possibilities for theta, you should expect to have a set of size theta. So S1 is a set of size theta. So S1 is a subset of S of size theta. Now, you fix f0 of y to 0 arbitrarily. You have the opportunity to do that because of this equivalent tuples of functions. And you will find one equivalent tuple of function f0, f1, f2, mapping this y to 0. since you map y to 0, so you can compute the value here, so you can compute the value there, so you can compute the value c, which is here, and you know the value z, it's belongs to ciphertext, so you will deduce the value which is here, and since you know the input of f2, you know one t mapped to one output in f2. Okay, so you deduce a value t here. You have actually theta values t for which you can deduce the output by f2. So with theta values of t, you can have the value in the table f2. Next, you will take the subset of S of all the tuples which use one of these value t that you have recovered. So you have theta values of t. In this set of size theta square, you are expected to have now a subset of size theta square. So S2 will be a subset of S of size theta square, where all the t which are represented here have a known output by f2. So since you have known output by f2, you can deduce the value c, and then deduce more values in the table of f0. So you deduce more points in f0, so now you have theta square values of y that you know for f0. So you can iterate, so now you take S3, which is a table of the set of all the tuples for which you know the value of f0 of y, and you will have a set of size theta cube, and you iterate like this, you play a yo-yo game like this, you encrypt, decrypt, etc. And after iterating, you will recover the full tables. Or maybe you will be stuck at the end because it doesn't make your set grow up anymore. So what it means here is that essentially, if you can model the behavior of this attack as a graph algorithm. So imagine a bipartite graph in which in one set of vertices you have all the possible values of y. In the other set you have all the possible values of t. So what this algorithm is doing is that it picks one random y, and it looks at all the t's connected to this y, and then from all the t's obtained, it looks at all the y's connected. So what this algorithm is doing is that it finds a connected component in a bipartite graph. So S defines the bipartite graphs with n with two parties of n vertices and theta n edges. This graph is random. So if you look at the series of random graphs, you will see that this graph is fully connected if the value of theta is around log n. So if theta is around log n here, it means that it's fully connected, so you will recover the entire tables of f0, f1, f2. And if theta is much smaller, say theta very close to 1, it's with high probability it has a giant component. So giant component means that you will recover partial tables for your functions, not the entire table, but you will have a substantial subset of your graph. Okay, so that's the 3R attack, the attack on 3 rounds that you can do by a non-plain text attack. Now we move to the attack on 4 rounds. It's a bit more technical. So here is a 4-round Feistel scheme. So you will have also some tuples x, y, z, t. For the attack, we define a set V, that's a set of pairs of tuples. So you have pairs of pairs. So a tuple is a pair of plain text and ciphertext. So you have pairs of pairs here. So you have 2 plain text, x, y, x prime, y prime, and 2 ciphertext, z, t, z prime, t prime. And V is a set of all the pairs of tuples which share the same value for z. So here z prime is equal to z. And the difference between t prime and y prime is the same as the difference between t and y. Okay? So let's consider the set V of these pairs of tuples. Actually, you're interested into a subset of this set, which is a set V good. It's a set of all the tuples for which z prime is equal to z and c prime is equal to c. Imagine that c prime is equal to c, so it means that here you will compute f1, the value of f1 will be the same, And since z prime is equal to c, the value at the output of f3 will be the same. So that's why the difference between t and y is equal to the difference between t prime and y prime. So this set v good is including the set v, for sure. Now, why is this set v good interesting? Because once you have c prime equal to c, you deduce that f0 of y plus x is equal to f0 of y prime plus x prime. So you will have an equation in f0, and you will deduce some information to reconstruct the table of f0. Unfortunately, you cannot construct this set v good. The adversary cannot construct this set v good because it doesn't know the values of c. Okay? But the adversary can construct the set v. So the adversary constructs this set v of pairs of tuples, and in this set of pairs of tuples, it's interesting to figure out who are the good pairs. So the principle of this algorithm is to construct this set v and to look for pairs of for the good pairs. So in this set v good, we have seen that x minus x prime is f0 of y prime minus f0 of y. So this suggests to define the label of this pair to be equal to x minus x prime. Okay? So in this set v, we define the label. So these elements of v, which are pairs of tuples, they will correspond to a vertex in a graph, and to each vertex we assign a label, which is the difference x minus x prime. So now if we look at these vertices, we'll find some edges between the vertices. Okay? So now this is a vertex. So you have a tuple, which is a vertex, another vertex here. You will link these two vertices by an edge if the y2 value, which is here, is equal to the y prime value, which is here. So if this y here is equal to the y here, you say that the two vertices are connected. Why do we do this? Because of the property that if you have a cycle now of vertices, so imagine that you have several vertices v1, v2, vl, and if it is a cycle, so it means that v1 connected to v2, v2 connected to v3, etc., and vl connected to v1. So it means that the y which is here is the same as the y which is here, the y which is here is the same as the next y, etc. Then, and if all the vertices are in v good, then you have this property, and when you sum the labels, since all the values of y are chained, it will sum to 0. Okay? So the property here is that if you find a cycle in v good, the sum of the label is 0. So that's a property of the vertices in v good. So the principle of the attack is to construct this graph and to look for cycles which have a sum of label equal to 0. And when we have a sum of cycle equal to 0, we will suspect that it comes from the properties that all the vertices are in V good, and this way we will find good vertices. Okay, so that's how the attack works. To see it precisely, it's more technical, so we have to prove a few lemmas. So first we have to figure out how many vertices are good in the set V. We can easily obtain that nearly half of them are good. So it means that if we pick one random vertex with probability 1/2, it is a good one. The problem is that we cannot identify which one are good, which one are not. Another property is that if you have a cycle of length 2, which is non-trivial, so non-trivial means that you don't just swap the two plain text in a tuple, and if the sum of labels is equal to 0, if the two labels sum to 0, then the probability that both vertices are good is larger than this number, which is close to 1. So if n is large, you see that this number is close to 1. So it means that if you find a cycle of vertices with 0 sum of label, it means that you have found good vertices. And you can deduce information about the tables. There is also conjecture that we have verified in practice, is that if you have a very long cycle which sum to 0, and when the plain texts are non-repeating, then the probability that all vertices are good is close to 1. And with this, we can mount our attack. So our attack works as follows. We first collect tuples. We create the graph. We find cycles of length L with 0 sum of label. And then we deduce some relations like this. The label of the vertices equal to the difference between the F0 of the Ys. Then we have lots of equations in F0. Then we create another graph to say when to connect the Ys when they are connecting by an equation. We look for a big connected component. We assign F0 of Y arbitrarily because we want to find an arbitrary, an equivalent tuple of functions. Then we deduce the value F0 of Y in this connected component. Then we apply the three. So since we have found F0 of many Ys, we can remove one round of the 4-round Feistel scheme. Then we have some known plaintext and ciphertext in a 3-round Feistel scheme. We can apply the previous attack, and we obtain F1, F2, F3, or at least a partial table for F1, F2, F3. With this partial table, you can decrypt all what you know as a ciphertext and iterate and play a yo-yo game again. And at the end, you recover the table of F0, F1, F2, F3. So we implemented this attack, and as a result, when we look for cycles of length 3, and we fix the value of m here equal to this number, so n is the size of the 2 branches of a Feistel scheme. So imagine here that you encrypt a number between 0 and 63. So messages are pairs of numbers between 0 and 63. We have tried this attack nearly 7,000 times, and it worked with probability of success 74%. Okay, so it works in practice. And actually with a complexity which is not too high. So now we can show how to break the FF3 algorithm. So FF3 algorithm, that's a format preserving encryption, which is based on a Feistel scheme and which has 8 rounds. So it's an algorithm which was proposed by Éric Brier, Thomas Perrin, and Jacques Stern. So it's an 8-round Feistel scheme where here in each round, so you have a tweak, and the tweak is split into 2 halves, the left tweak and the right tweak. And here you will use the right tweak and you will XOR it to 0 for this round. And on the next round, you take the left tweak, you XOR it to 1, then the right tweak, you XOR it to 2, etc. That's the Feistel scheme in FF3. Now, XORing the tweak with the index number is a terrible idea, because the adversary can modify the tweak. So let's see what happens if the adversary changes the tweak. So the tweak is TLTR, and if it XOR 4 to both values of TLTR. So you have here your encryption with the tweak TLTR, and on the right half you will have the same when you have replaced TR by TR XOR 4. So if TR is replaced by TR XOR 4, here you have TR XOR 4 XOR 0. TR XOR 4 XOR 0 is TR XOR 4. Here TL is replaced by TL XOR 4. So here it should be TL XOR 4 XOR 1, so which is TL XOR 5. And here it will be TR XOR 4 XOR 2, which is TR XOR 6, etc. So what you observe here is that the sequence of tweak which is used in the first 4 rounds is TR XOR 0, TL XOR 1, TR XOR 2, TL XOR 3, is the same as the sequence which is here. Okay? The sequence here is the same as the sequence here, and the sequence here is the same as the sequence there. So it means that this part here, the first half of the encryption, we can call it G, and here you have the function G here. So the function, the encryption with the tweak TLTR is a function G composed with some function H, and the other one with the other tweak is a function, the same function H composed with the function G. So it means that the adversary has the opportunity to make some chosen queries to G composed with H and to H composed with G. That's quite terrible from a security viewpoint. So what can we do to break this? we have actually an attack. So the adversary can play with H composed with G and G composed with H. And the adversary can collect actually many chosen inputs and form some sequences. So he can choose, for instance, some X0, and he will apply repeatedly the encryption with a tweak T, and he will construct like this a sequence. And he will do the same with the other function, with a tweak T XOR with 4,4. Okay, so how is the attack working? The adversary chooses A starting points at random, x10, x20 until xa0, and he will encrypt repeatedly with a tweak T to make a chain of length B. So he will make like this 8 chains of length B. So he makes A random chains of length B, which comes from the iteration of H composed by G. And he does the same with G composed by H. He chooses A starting points, and he makes A chains of length B. After that, he has to guess. For instance, he guesses that this value, if you apply the function G, you obtain maybe this value. So imagine that G of x10 is equal to x prime 22. What happens? You know that G composed, if you do H composed with G on x10, you obtain x11. So it means that if G of x11 is x prime 22, it means that H of x prime 22 is x11. And then G of x11, it must be x prime 23, etc. So this is what's happening. So if you imagine that this is mapped to this by G, then this will be mapped to this by H, and this by this by this to this by G, etc., etc. Okay. So like this, if you guess that G of this is that, you will deduce many pairs of input-outputs to both G and H. And G and H are 4-round Feistel scheme, and you can apply the previous attack. So this is how it works. So the algorithm, more precisely, so you have the tweak T prime, which is T XOR 4,4. Then you make these 8 chains of length B. So you choose the starting point, and then you encrypt repeatedly for both tweaks. And then for every I prime j combination, you just assume that G of xij is mapped to x prime I prime 0, and you run this 4-round attack. Maybe it won't work because it comes from a wrong assumption. If it doesn't work, you just iterate. And if it happens that you have such an equality, then you will be able to break the entire Feistel scheme. Okay? So that's how it works. And actually, to analyze this algorithm, you have to figure out what is the probability that one such assumption works. And for that, you have this magic lemma that if you take a random permutation G over Zn squared, if you take 2 starting points x0 and y0, and if you define the sequences of the chains of length B starting from x0 and y0, the probability that these 2 sequences overlap on at least a chain of length m will be this number. So imagine that you have this chain coming from the x's. So, okay, so the chain of length B is here. Here you have a chain of length B starting from x0. So the probability is that when you pick y0, it will create a chain which overlap on a chain of length m. It's the probability that you choose y0 in this subset here. If you take y0 here, you will overlap on the first few m values of the chain of x. So that's a probability. And if you select b equal to 2m and a equal to n over square root of 2m, this probability is quite good. So you can apply the attack. We implemented the attack, and with, again, L equal to 3, we have run the attack 10,000 times, and we have obtained this probability of success. So for very low n, you have strange phenomena happening, so it doesn't work, but maybe you can find other attacks. And for regular n, it works with quite good probability. And I'm pretty sure that we can still improve the attack Actually we wanted to show that there is a security problem and that FF3 is badly broken by this method. So to fix this, it's quite easy. So remember that all the problems, all the troubles came from the fact that in FF3 we XORed the index number to the tweak. Okay? So instead of XORing, if we just concatenate, then this attack cannot work at all. So that's a very easy fix. Instead of XORing, we will concatenate. Okay? So we concatenate, and then we have a repaired FF3 algorithm that we call FF3 star. Okay? So that's for the attack we presented at the crypto conference. Now the NIST is wondering how to adapt the standard. Since then, we continue to work, and we wonder what is the cost of generic attacks. So now we don't try to use any bad structure of the Feistel scheme of FF3 or FF1 and so. We just take an arbitrary Feistel scheme and try to break it. So that's how to apply brute force. So I like this title, which was published in the communication of ACM, and so it was not related, but the science of brute force. So the best attack we have found in the literature to brute force the tables of FF3, that's actually the meet in the middle attack. In the meet in the middle attack, we have some plain text, some ciphertext. So we have some plain text ciphertext pairs. So you have Q pairs. What we can do is that we can brute force all the function in the first R/2 rounds. So we enumerate all the possible functions. So it's huge, it's double exponential, so that's terrible complexity. But imagine that n is so small that it's feasible. So you do a brute force on the function in the first R/2 rounds. You compute the value in the middle. Then you do the same from the ciphertext. You brute force all the function in the last R/2 rounds. You compute the z's. And if there is any match in the middle, if there is any meeting in the middle for this vector of z, then you can deduce some possible set of functions which encrypt the plain text into the ciphertext. So that's the algorithm which is here. That's the basic meet in the middle algorithm, and there are tricks to improve it slightly. Okay, so maybe I will explain this on a picture. So in a picture here, to improve it first, the first trick is that since you can have a chosen plaintext attack instead of a non-plaintext attack, maybe you can choose plaintext such as R0 doesn't change too much. So if R0 doesn't change too much, you don't have to enumerate all the F0 of all inputs. So you have only a partial tables of F0 to enumerate. So that's the first trick. Second trick is that somewhere in the middle, so there is this function F4 that we remove. Instead of meeting on all the pairs here, the value here and here, you can only try to meet on this value. So we'll have maybe more solutions and some bad solutions, but after you have some potential solution, you can eliminate with other tests. So if you meet only on this value, then you don't have suddenly the function F4 to enumerate. So you have one function less to enumerate. And finally, the last trick is that instead of trying to meet on a value between 0 and n-1, you can decide to meet only on one bit of information z. And then on F3 and F5, you don't have to enumerate all the function from n to n, but only from n to 1 bit. So you have n inputs mapped to 1 bit. So you have less to enumerate for F3 and F5. So with all these tricks, you have a complexity which is still very large. It goes super fast, but for very low values of n, it's feasible. Now we have found another way to attack by brute force, which is not based on a meet in the middle, but which is based, so instead of trying to enumerate the entire tables here and here, what we do is that we try to enumerate partial tables, and we try to make some partial tables which grow up in a pool. So that's the strategy that we will apply. So first, let's have some definitions. A function is defined by a table. Now we will consider partial tables. So it's a subset of the table of a function. partial table is a subset of the table. A tuple will be consist of R partial tables. So we'll consider tuples of partial table defining the round functions. Now we say that a tuple encrypts a plain text on S rounds if there exists a sequence of xi's such that the plain text is x minus 1, x0, and if you have this relation. So it means that the partial table is defined for every entry which corresponds to each round. So you can start encrypting with partial tables, and you're not stuck because you have always the right value in the partial tables. So a table encrypts a plain text to S rounds. You can also define that the plain text encrypts the plain text into a ciphertext. It will be the same with S equal to R and the ciphertext equal to X R minus 1 X R. So that's pretty natural. You have the same definition for decryption. We define also what it means for a table to evaluate a pair plaintext ciphertext for all but K rounds. So it means that there exists some S such that you can encrypt P to S rounds and not more, and you can decrypt C to R minus S minus K rounds, but not more. So it means that if you go from plaintext and a ciphertext, you're stuck somewhere, and the number of rounds which is missing is equal to K. Now you say that a tuple is compatible with a pair PC if either the tuple fully encrypts P into C, or if you can compute this pair PC for all but K rounds with some K at least equal to 2. So if you are missing 2 rounds or more, so it means that you will be able to complete your partial table so that you encrypt P into C. Or if you can compute PC for all but 1 round, and you have a special equation in the middle, some matching, saying that the round which is missing, you will still be able to complete it so that P is encrypted into C. That's what it means for a tuple to be compatible with a pair PC. Okay, so with this definition, we can then show the algorithm. So at the beginning, you start, so you have this list of plaintext and ciphertext. At the beginning, you pick an arbitrary tuple, elementary tuple, it's a minimal tuple, which encrypts P1 into C1. So on P1, you will wonder what is the value of the function f0. You take it arbitrarily. Then you wonder what is the value of f1. You take it arbitrarily, etc. You make sure that P1 is encrypted into C1 with this partial tuple, and you put it in this T1. So T1 is a partial tuple which encrypts P1 into C1 and which is minimal. There is only 1 point defined in each round. So you define your pool of tuples to be limited to this tuple, and then you iterate, and you will make some pool which is growing from one iteration to the other. So actually, pool I will be a set of all the minimal extension of this initial tuple T1, which encrypts the first I pairs and are compatible with all others. So we'll try to encrypt 1 more pair at each iteration and remain compatible with all others. So at the beginning, you initialize pool I to empty, and you have a loop for each tuple in a pool I minus 1, the previous pool. You look at how to extend this tuple so that you encrypt Pi into Ci. So you will obtain a tuple, many tuple T prime, and for these tuples, you check if they are compatible with the other pairs, and if they are, you add it into pool I, and you iterate. So what happens with this algorithm is that you have some pool which grows very, very quickly, and at some point it will be stuck, and it will start decreasing, and at the beginning you will have just one solution. So that's a set of tuples which encrypt all the PIs into the CI. Okay. The analysis of this algorithm is quite technical. I just show you the formula to estimate the size of the pool at each iteration. So the size of the pool at each iteration can be estimated this way. So what is here? N to this power, so theta in, so imagine that that's the number of points on which each round function is defined. So you have theta I n points on which a function, each round function is defined. You subtract 1 because of this initial tuples that you fix arbitrarily. You multiply by r, and that's the number of values you have to define. So n raised to this power, that's the number of possible partial tuples to consider at iteration I. You have to divide by 2 to the power 2i minus 1, which is the probability that you encrypt each plaintext with ciphertext for the first I pairs. Then here you will have to estimate for how many of the remaining pairs you encrypt for all but one round. Okay, so if you encrypt for all but one round, the probability is this. That's the number of pairs. And for each of these pairs, you will have one equation to satisfy. So this is why you have subtraction here. And finally, that's the number of additional pairs for which you can fully encrypt, but the probability that the encryption match the ciphertext that you know is defining two equations. So that's why there is a 2 here. You have also a constant to adjust size of the pool at iteration 1 equal to 1. And the theta here, which I didn't define, that's just the probability that one entry is defined in a round function. So with this formula, you do the analysis, and you can estimate the complexity of the algorithm. You have more tricks, again, like extend to a chosen plaintext attack, add more entries when you can deduce them in partial tables. Do also some earlier bots. If suddenly your pool becomes too large, then it's better just to stop the attack and maybe restart it. And also you can order the pairs in some optimal way to speed up the algorithm. So now we have two algorithms, two generic algorithms to break Feistel schemes, the meet in the middle and this one. We can try to compare them. Okay, doesn't work so well. Okay. Asymptotically, the meet in the middle attack works with this complexity. So it's essentially n to the power r half minus r half times n, so minus something because of all the tricks that we discussed. And our algorithm works with a lower complexity asymptotically. So you see that it's n to the power 1 minus something compared to this n to the power 1. So it works with a beta complexity, but in practice, this attack is better when n is not too small. Okay, maybe this is running out of battery. Okay, so the algorithm with a pool needs more data to succeed compared to meet in the middle. Meet in the middle is optimal in the sense that it works with best data complexity. With our algorithm, we need more data to make it work better. So the pool algorithm can have a lower complexity in general because of this asymptotic behavior, and in practice it works for r less than 10. So here you have the graph here, the graph of the complexity. You have the value of r, the value of n. In this region, the meet in the middle is better, and in this region, our algorithm is better. We also plotted here that the curve of all the parameters for which we have a complexity which is 2 to the power 128. So remember that the NIST standard was aiming 128-bit security. So to be secure, we should be above this curve here. So we should be above this curve. So it means that there are some parameters here that we can break. So in practice, if you take 8 rounds, like for FF3, you can realize that for n equal to 2 to the 4, n equal to 16, so 2 to the 16, n equal to 16, that's a parameter which is allowed in the standard. So remember that n has to be at least equal to 10. Our algorithm has complexity to the 116. So it's still huge, but it's below 2 to the 128. So we can see here that the number of rounds is not enough to have 128-bit security. You can also compare the complexity of meet in the middle with our algorithm. You can see that our algorithm is better, but these numbers are so high that it doesn't mean so much. Okay. So to conclude, so we have seen that Feistel scheme over a small domain, there is still some research to be done on this to understand the security. We have seen that a bad domain separation construction in the algorithm FS3, but we can fix it. And we have also seen that 8 rounds is not enough to be secure against generic attack. So to be more secure, we should have at least 10 rounds and make sure that the domain separation is good enough. Or increase the minimal value of n. Thank you very much.
Any questions? I have one then. You said that the pool size sometimes increases and then stabilizes. Do you have any short explanation for this behavior?
Yes, so actually the problem is with the formula that I've shown you. So you have a formula. Doesn't work. Okay, so you had a formula for the size of a pool. And with this formula, you can see the evolution of the size of a pool until it reaches a maximum and then it starts decreasing. You can also estimate how many rounds you need to obtain this critical size of the pool. And you can also try to compare it with practice. So this is what we did. So that's all in the paper, but I don't have the figures here.
Any more questions, please? Okay. Let's thank again, Professor.
Thank you.